what we can actually, instead of just a normal bit, which can only address 1 or 0, we can actually address all these myriad of in-betweens, and we can actually measure. We're using complex numbers and imaginary numbers. We can measure, which is why we can operate so mind-boggling quickly. And to give you an idea, when we have this is a bit in the future, but when we have a quantum computer with 300 pure qubits, we will be able to map to every atom in the observable universe. So that's how amazing it is. So again, I just want to get over the fact it's amazingly powerful, mind-bogglingly powerful. And already quantum computers, a thing called quantum supremacy, quantum computers have outperformed the fastest computer on Earth. So that's where we're at. I'm now going to pass over to Koen.
Yeah, you just once he starts talking, you'll be going through this series.
Okay, Koen, if you're ready, you can take over and take it away.
Okay, thank you very much. Welcome everybody. Thank you very much for inviting me to give this talk. I will be. I'm now around 6-7 years active in quantum computing. I'm a computer engineer from my background, so I was supposed to think about what is the global structure, architecture that a quantum computer should have, and that's what we did. But then I discovered that the quantum physics, and it's not like I want to insult anybody here, so I just try to be very neutral in my observations. Yeah, that they still have to make so much progress, substantial progress, one, in making a choice in how to make a qubit, a quantum bit, because we still have like 6-7 technologies fighting against each other, and it goes from diamonds to Majoranas to semi-conducting, superconducting qubits, and so on. Yeah, and that really still needs to substantially improve. And so that's why I decided at some point that I will start focusing, let's say, on a more, let's say, more pragmatic kind of approach, which is to build a quantum accelerator. So not like the universal machine that will do everything that you want, yeah. But say no, we're going to look on one specific kind of, in our case, medical kind of needs, yeah. But it can be in communication, it can be with interaction between machines. Or anyway, so there are various ways in which you could still develop quantum accelerators, and that is also the way that modern machines are developed these days. So my title, so I will say a couple of things about the title. Yeah? First, the topic: virus, vaccines, genes, and quantum. I will try to explain that a little bit. Iman, he mentioned Aritra. He's one of my PhD students. Well, actually, he's maybe the only second PhD student that I have now. 4 already graduated, yeah, but I'm left now with 2 people, Aritra and Anuriet. And so Aritra, he's the one working really on the quantum algorithms for genomics, genomic analysis and sequencing. There's also a name that you see here at the top of my slide, yeah, it's BlueBee. And I will say something about another company I started, but that will be on the slide. But BlueBee is a company that I want to start looking at quantum and genomics. And I will explain what the reason is. And for some reason, Iman already mentioned it, that I will move to Portugal because I'm Belgian by nationality. And the University of Porto also wants to move into quantum computing. But basically nobody's doing anything yet there, so they try to pull me in, and I can contribute to that particular thing. But I said my main priority is developing QB. Yeah, so that is why these things are mentioned. And of course, here's a little subtitle: the world cannot afford a COVID-29 because we have COVID-19 as we have it right now. Yeah, and it related to that are trillions of money that we need to spend, yeah, on having all of the economic impacts that we need to take care of. And economic, that means societal as well as health and other things. Yeah, that is what I understand to be that will consume these trillion amount of euros or dollars or whatever currency you want to go for. Yeah, so that is the big background. Genomics, I will say something about it later on, but genomics, we do see a trend in substantial downward scaling of the cost of doing one genomic analysis, or let's say to have your personal genomic profile, because where let's say 20 years ago it was around 100 million to do it, and now we're around 1,000. Yeah, now these numbers, they're always kind of a bit strange, but we do see a substantial trend downward, even faster going down than Moore's law, computing the number of transistors that we can have, let's say in any modern chip, CMOS chip that we're making these days. So that is the context of why we're doing. Why genomics? Because I started, and I pulled in, of course, several colleagues later on. Yeah, I started a company called BlueBee, and if you type it in your on your website, bluebee.com, you will still see it's online. And it was, and this is very new information, but I'm allowed to say it because it was already published in a newspaper in Belgium and in the Netherlands this morning. BlueBee was bought by Illumina, and maybe you don't know Illumina, but it's a $90 billion company producing several billions. I'm sorry, the 90% is more. 90% of the DNA sequencing is done in the world is based on the Illumina machines, and so they were so enthusiastic about the software that we developed inside BlueBee that they decided to incorporate that in every Illumina machine worldwide. So we're a relatively small company because we're only like 30 people, yeah. But we were bought by Illumina, and I got that news just 4 days ago on Monday. So I was not supposed to say anything, but now it's on the news, and so now I can say something about it without interfering or insulting anybody, of course. Yeah. So that is basically what BlueBee is doing. And here you have an overview of, let's say, the internet-based offering of the genome sequencing kind of algorithms. Yeah, and it's basically all over the world. We don't serve Africa yet, unfortunately. Yeah, and only one city, Sao Paulo, in Latin America. And of course, yeah, there's China and Russia and many other countries are not involved yet, but that will keep on growing. Yeah, and I do hope that you realize that genomic profile, the genetic basis of every single human or other living organism is going to be the basis for any medical diagnosis and even medication in the future. So it's extremely important that we really make substantial improvements in that field. So that's why I decided, and that is quite recent, with a Dutch friend, yeah, Karel. I will not say the personal names, but I decided to start maybe QB, Quantum B, QB. So from BlueBee to QB, my youngest daughter, she came up with the name actually. Yeah, and so that's what we decided to do. And here you simply see it's a printout of the website of a big journal. Well, big journal. Flanders is a very small country, right? But a journal in Flanders that published the purchase by Illumina of BlueBee. Yeah, so in that sense, it's no longer a top secret. Yeah, and I can keep on working now on genomics, but from a quantum point of view. Yeah. I understood, well, I asked Iman and he said, like, no, people should be aware of what the basic concepts are. But again, we're bringing here so many different things together. So I just want to give a quick resume of the concepts that I will be using, especially the quantum concepts that I will be using maybe regularly. But first, let's look at the genomic kind of words, and it's genotype and phenotype. And these are two main concepts. The genotype simply means we're all human beings, so we all share the same human DNA. Yeah, so that's the entire set of our genetic profile. And even though we may all look a little bit different, that is maybe due to maybe 1% the genes that we have, in which we are a bit different. That's why there are men and women, no hair or long hair like Eamon, yeah. But you can also have phenotypes, and these are basically the observable characteristics. So the color of the hair, the color of the eyes, the size, how big or how tall you are. Yeah, so those are the main things of the, let's say, the genetic background. And it's a huge field, so I cannot claim in any particular way to be an expert on that. Yeah, I'm not even an expert on quantum. Yeah, I just try to understand what quantum is, and after 6-7 years, I start understanding a bit what those concepts are. And so the concept that I will be discussing mostly is these quantum bits that we abbreviate to qubits. Yeah, and one qubit, let's say the psi qubit, is consisting always of 2 layers. Yeah, it's a 0 and the 1 layer, and it can be a plus and a minus. But yeah, we kind of restrict the complexity of these qubits to only 2 layers. Yeah, in computer science and in computer engineering, we're also used to 0 and 1s. Yeah, but only 0 or 1s. Yeah, and here we have a 0 and a 1 state, but they have also a parameter, this alpha and the beta. Yeah, and we call them amplitudes. And if we combine, if rewrite these amplitudes like we do here, yeah, I can actually, I can. Aritra told me how to do that. Yeah, so I try to illustrate a little bit what I'm talking about. Yeah, if you rewrite these amplitudes in this particular way, you get 100% probability. So that basically means these amplitudes, they sketch or they compute the probability with which either I can draw a 0 result or a 1 result. Yeah, and this alpha and this beta, they represent the probability with which that will happen. Because let's not forget, when you do the readout of a qubit, and that is in the quantum physical world, and when I give my quotation mark, that means like, yes, this is the theory, yeah, but we're not there in practice. Yeah, you basically destroy the superposition. So if I have 2 qubits, yeah, no, if I have 1 qubit in these 2 states, I will only read one of those states, yeah, the 0 or the 1. And the probability with which I can do that depends on this alpha and this beta. That's why quantum computing is also always like repetitive computation. So you never do only one run of the same algorithm. Maybe you need to do it 5 times or 100 times. Nobody really knows how many times, but then you get some kind of histogram of the measurements, and that the ones with the highest frequently measured one is the most likely correct solution of your algorithm. Yeah. You can also combine these qubits, because I just mentioned now 1 qubit consisting of these 2 states. If I'm combining two qubits, so I can have 4 states, that's 2 to the power 2. If I can combine n qubits, I have 2 to the power n. That's what Eamon already just said. Yeah, if I have, let's say, up to 300 qubits, and I would say which qubits we're going to be working on, I have 2 to the power 300, which is a number bigger than the estimated number of atoms in the known universe. And trust me, there are more universes than just the one in which we are living. Yeah, so that is important to understand. Now, why am I interfering, or why am I combining now quantum computing and this genetic kind of thing? Yeah, and I'm repeating now a bit what Eamon said. Yeah, quantum computers, yeah, they're not there. Let's be very clear. Yeah, they are not there at all. Yeah, it may take another 10, 15 to 20 years. Yeah, I may disappoint. I know there were people from Atos. Yeah, I will only say one thing about Atos, that's on a slide later on in my talk. Yeah, but there are so many problems that we still have to solve, and so I cannot say that we can have a quantum computer, let's say, in the next 5, not even 10 years. Yeah, so that's why I decided also to go to accelerators. An accelerator performs one particular function. Yeah, and just like in many applications, that's why modern computers are always constructed with co-processors. Yeah, and it can be well, I said the genome chip, no, but it can be an FPGA, can be a GPU, a TPU. Different kinds of technologies are available, and why not a quantum accelerator, quantum chip at some point? Yeah. So what is it that we need to make a quantum accelerator? Of course, you need always these qubits, because without the qubits, you could not represent the quantum information that you want to manipulate. Yeah, but you really need to know what is being used now to make a qubit. Is it an Majoranas? Is it a diamond? Is it superconducting? There's still it's like an open field, yeah, and everybody's fighting with each other, yeah, and it's normal to fight in science, yeah. But the quantum physics people, they argue among themselves a lot that they're the best or whatever it is, yeah, and so that also depends on how good will those qubits be. Yeah, and there is not a single technology from ion traps. Yeah, was very popular, let's say 10 years ago. Now superconducting are popular, and maybe semiconducting will become popular in 5 years from now. We really don't know. Yeah. In any case, what I do think we will know is what I've been doing. And when I say it's never me myself, but we had a team, yeah, to work on those aspects. Yeah, the full stack. Such like in classical machines, you have some kind of an application. There's a programming language, there may be an operating system, there's a microarchitecture, and then there may be your accelerator chips. Yeah, so that is what I think we also need for a quantum accelerator. So I will give more information. Well, actually, I already give the overview of what I think we do need for a quantum accelerator. Yeah, all of the aspects that we've been working on. And I will not talk about all of them because I don't have that much time, and I don't want to disappoint everybody or discourage everybody. Yeah, but I do want to mention here the tensor mathematics. Yeah, all of the mathematics well, mathematics is a dominant language, is a universal language, and also quantum phenomena, they can be described in a mathematical way. In how? Well, it's tensor mathematics. Yeah, and I will not talk about these things because this is a very specific way of combining matrices and doing operations on those matrices. Yeah, but I will say maybe a little bit about the programming language. Algorithm design is what I will talk about today, which is basically Aritra's work. Yeah, operating system, maybe it's a bit too early, but it's definitely an interesting field. I will only show one slide about the microarchitecture. We also need mapping and routing, but I will talk about that when I present our platform. Yeah, and the platform is basically then this one that we've made ourselves. Yeah, and if ever there's a good chip available, a real physical chip, we will use it too. But I'm not expecting in the next 5 to 10 years that any reasonable chip will be available. So that is basically what our outline is. The big picture for the quantum field, quantum computing field, are these two graphs that I showed. Yeah, and maybe I'm completely wrong, or maybe I'm right. I don't know. Yeah, but I made them in last year. Yeah, and here we have, let's say, the gray kind of thing is what the quantum physics people are doing, and computer engineers, we're basically looking at those as we did those things the first 4 or 5 years. Working with Leo Di Carlo or other people in the lab in Delft, yeah. But then I realized that it's still so much work for them to do anything meaningful for us that I started looking now in a different direction, so more in the software layer, yeah. And so really I'm looking now about maybe companies have a particular kind of idea of their particular need. So we need to translate that into quantum logic, yeah, and that's why we need also programming language, and then ultimately have some kind of implementation on a quantum accelerator, and it's only here, yeah, from this dotted line to there, that it makes sense that we start to talk to the physics people again, because then the qubits here might be good enough to do some testing, but we are still here, yeah, and so here. There is absolutely no particular interaction that I need or that I actually want, yeah, with the quantum physics people. So that's why I will present also in this slide the presentation of the platform that we're going to be using. Yeah, Gartner. I'm assuming that everybody knows Gartner, which is an IT consulting company from the US. Yeah, and they've been very active in looking at all of the innovating kind of technologies popping up, and they came up with this particular hype cycle, yeah, which is where everybody is super enthusiastic and wants to be the main player on a particular field, yeah, and you see whatever was very interesting. It's close to reaching maybe here the top of this first cycle. Yeah? Quantum is there, yeah, in red. Yeah, it started pretty low, and every year you see it growing, and you know that companies like Google, IBM, Intel, they're all jumping on quantum, yeah, until they reach a point, yeah, and that's why it's a cycle, it's a hype cycle, where they see like, wow, it's still another 10 years or 15 years away. Yeah, so we still have to maybe the many companies, they don't want to keep on putting money into this thing, and that's why the interest will go substantially down. Yeah, and it's only at a later phase when other companies will start moving again in the direction towards an implementation of, let's say, a quantum accelerator, and at some point, maybe much further down here, yeah, quantum computer may be possible. So that is not my invention. This is an observation from other people who look at the field in a very general way. Now, what is it that we've been doing, and that we want to be doing is phase 1 and phase 2. And actually, whatever we did in phase 2 should actually be called phase 1. Should be maybe a small little cube here is phase 1, because is phase 0, because we programmed a language OpenQL. We did an instruction set architecture. We made a microarchitecture, but we did that looking at these kinds of qubits, basically those the super and semiconducting qubits. Yeah, because I think our team was instrumental in attracting Intel to finance the research, the quantum research in Delft. Yeah, and of course that was primarily looking at super, but of course being a semiconducting company, Intel is now more and more looking at semiconducting. Yeah, so in that sense, yeah, this should be called phase 1, should be a little cube that I put here on the top left side. Yeah, but we're now working in phase 1, and maybe we will move to phase 2 whenever any of those quantum chips will be sufficiently good so that we can actually use them in our quantum accelerator setup. Now, there's one concept that is important that I will talk about is a perfect qubit. Yeah, because if all of the qubits are so problematic, yeah, then that means the error rates of the qubits are. Wait, I have to see because I have some slides now. I'm looking at another computer, so that I see a little bit. Yeah, okay. I will talk about that actually here. Yeah. So we do see that qubits, we need them. Yeah, and we have real qubits, but we have to make them realistic. So they have to be substantially improved in quality. Yeah. Whereas in CMOS or classical hardware, we used to have errors every 10 to the minus 15, minus 16 operations that we do. Then we have one error. In quantum physics, we have 10 to the minus 2, 10 to the minus 3. So it's every 100 or 1,000 operations that we get a substantial error. Yeah. On top of that, yeah, these qubits, they decohere. So they basically go back to the ground state. I put them in a particular state, and in nanoseconds, boom, they're in the ground state. So that means I lose all the information. Yeah, so I have to keep them alive to maintain them in a particular state. So that is already a challenge in itself. So it's not that the physics people, they have an easy job. It's a very difficult job that they have to do, but I cannot wait for them to get any meaningful results that we can use to build, let's say, a quantum accelerator. Yeah. On top of that, you have error rates. Yeah, I write that here. Error rates. So they have to make rotations. The block sphere is the big ball. Yeah, and you make a single qubit rotation is a particular angle. Yeah, in this block sphere. Yeah, either you overshoot the angle or you undershoot the error, the gate operation. So that means it's never going to be, never going to be accurate. So if I'm used to having 10 to the minus 15 and I'm 10 to the minus 2, I want them to show that they're maybe reaching 10 to the minus 5, 10 to the minus 6, because that is a big challenge for them. So that's why I said, I'm going to change our vision. And that's why we said, we're going to work with perfect qubits. Yeah. That means no decoherence. If I put them in a particular state, 5 days from now, they're still going to be in that state. Yeah. No errors. If I make them do a 1 or a 2 qubit operation, it's going to be an exact operation in the block sphere. So that is very important that I highlight that as, because this also means that for companies and organizations, yeah, quantum computing is much more interesting to start looking at right now if you do it from a perfect qubit point of view. And I will come back to that later. So what is the outline? And I will try to respect the time, and I will see Eamon to say, hey, it's time now, whatever signal he will give me, yeah. But what is genome sequencing about? What is the quantum algorithm that we're currently working on? Yeah, what is then the microarchitecture? And what is then our testing platform? Because yeah, you can develop an algorithm, but if you don't really test it on real data, how can you know that your algorithm is correct? Yeah, so that's why we go towards supercomputing platform. Yeah. So okay, genome genetic profile is based on genome sequencing and genome analysis. That is basically the core of what people, and I'm talking now not about computer engineers, but I'm talking about biologists, medical people, yeah, genetic people. So they work on these chemistry people. They work on, let's say, the nucleobasis components of any DNA structure. Yeah, and luckily they're only 4, the CGAT. Yeah. Yeah, that are, and I cannot even pronounce these names. Yeah, but there are four basic nucleobases that together make up to, let's say, 3.2 billion kind of genome sequences. Yeah, for the human being. Yeah, and if you look at these viruses that I mentioned in the beginning, luckily they can be much smaller. Yeah, and Arita figured out that it's around, or other people figured that out. If I don't want to insult Arita, because if I refer to him, it's usually a compliment that I'm giving him. Okay, but it's around 30,000 nucleobases components, so not 3 billion. So that means even in a quantum context, these viruses are becoming analyzable. Yeah, with the algorithm that we may doing. Just to highlight a bit the importance of this analysis. Is not that we think we have all the solutions. Trust me, we know we have no solution. Yeah, we just want to initiate a path in which multiple people start joining, such that together, collectively, we start finding, let's say, analyzing a virus and maybe develop a vaccine for that. So here you see, of the last maybe 100 years, yeah, or even more, but let's take the last 100 years. Yeah, you see here. Yeah, all kinds of viruses that were contaminating people all over the world. Yeah, and now we know we have this fully interconnected economy, world economy. People are flying all over the world to every country, and that's why you get a very rapid spread out of, let's say, this COVID-19 virus that we saw from, let's say, November, December last year until today. Yeah. So, but we have SARS, we have MERS, we have Ebola, which is still a very big problem in Africa. Yeah, and you see they're around 50% death rates, fatality rates. So just imagine, yeah, that you have a sickness like SARS, which is at 10%, yeah, or MERS, yeah. So the death rates can be incredibly big, and I simply computed. And this is not to insult anybody, not from the World Health Organization or anybody who making claims, yeah. But I'm simply comparing, let's say, the Spanish flu here, yeah, that occurred in 1919, and that is right after the First World War in Europe, yeah. And we're around. I read 1.5 billion people, but I make it 2 billion people. There were about 15 million people dying by the Spanish flu, which was not originally coming from Spain. Yeah, let's be very clear. So that amounts to 2.5% of the people worldwide died of that one particular virus. So if we now look at this COVID-19 in 2020, so right now, yeah, and let's assume, and we are not there, but let's assume that we could have 2 million people dying, yeah. We're only at 440,000, let's say 500,000 people dying right now, yeah? But we have a population which was in 1919 only 2 billion, but now we're at 7.5 billion people. So it's 3 to 4 times as big, whereas we see it is even 100 times smaller, the death rate. So do we still have to be super careful about COVID? I said, yes. Because what we do see is that we are not prepared at all to handle any kind of deadly virus that will pop up in any particular case in the next 3, 4, 5, 10 years. We don't know, but it will pop up. And then we can have really a worldwide contamination and a death rate at worldwide. So that is for me a very important reason why I decided to continue working on quantum computing. Yeah, but I asked also Aritra, yeah, look at these genomic kind of things, and just as a small anecdote, his parents are medical doctors in India, yeah, and they're so happy that he's doing his PhD on quantum genomics. They said, like, this is the future for this. So that is already a perception that we do see that other people are having. This is a screenshot even I made from Mark Jackson's kind of talk. I was kind of a couple of weeks ago, yeah, in which he showed also some kind of movie, but I do not show the movie here, yeah, of some proteins and drug discovery challenges. And so I cannot even explain what we're seeing here, but just to make a link that whatever you organized in the past even, yeah, is still very relevant and to what we're currently doing right now with QB, yeah. And I'm talking about QB because as I said, I'm moving away to Portugal, to the university there, going away from Delft University to Portugal. Yeah. So I wanna highlight a little bit what this genomic sequencing is all about. Yeah. So let's assume that we have a reference genome, not of 3 billion, but of 32. Yeah. Let's just say 32. Yeah. And I have a short read here. Yeah. Of a length 5. So what is the genomic sequencing doing? This is what BlueBee has been doing and will be doing now inside Illumina. Yeah, and this is also what QB is looking at, is that we have to find a place where this short read is best mapped on the entire sequence. And if you look at the 3 billion, yeah, and we have millions or billions of short reads, yeah, that means it's an incredible computational platform. So what is the algorithm doing? Yeah, I'm so simply showing here, it's an illustration that Aritra made. Yeah, where this particular short read is fitting here, where the Hamming distance is the lowest. Yeah, and you see the Hamming distance is it's red, green, blue. Oh, here's the difference, and here it's 4. So it's kind of a very good mapping of the short read onto the overall reference genome, and so that is still a very active kind of way in which we currently do on a daily basis the genomic sequence of any human being or any other organism that needs to be analyzed. Yeah, so that I think is, and I will not talk about the qubits right now. I will do that later. Yeah, but this is basically what the idea of genome sequencing is all about. So let's scale it down. Let's say to make it representative, such that when I talk about the algorithm, the quantum algorithm, that you have kind of at least an intuitive idea of what it is that I'm talking about. And I sent a PDF also of the slides to Eamon. So if you want to have a copy of the slides, yeah, he can send it around. Yeah, so that I think is important. But let's assume that we have a representative genome, yeah, or a reference genome, but only of length 4. So that is kind of, yeah, may sound trivial, but the ideas stay the same. Yeah, and so you have red and green. Yeah, are the two basic, let's say, basis elements that we have. Yeah, and we can have a short read of length 2. Yeah, wait, I still have to, because this is a bit, I don't know whether you see that. Oh, okay, that's more interesting. Yeah, so I have a short read of length 2. Yeah, and then we have to find out where does that fit on this reference genome, and we can immediately see, like, okay, if this is the reference genome, yeah, the 0, 1 immediately fits on this and on that part. Yeah, so that's why this says it's the green flag. Yeah, and these ones do not fit. It's 1, 1 and 1, 0. Yeah, these are other possible combinations of the values. Yeah, and they don't really fit. Yeah, because we're talking here about the 0, 1, and that fits on this particular one. Yeah, and that is a bit the logic that I will try to explain in the rest of my slides. So the big picture that we're doing is actually is this one. Yeah, the one that is orange is basically the core of the work of Aritra. Yeah, and what is gray, other people have been doing that. Yeah, and of course we also we keep on working and making things better. Yeah, in a particular way. But I will point to most of those aspects during the slides. Yeah. So that basically means I have the split of the reference genome in the base components that I can have. Here I only 4, so that means 3 components. Yeah, I have to put them into some kind of database with an index 00 for this one, 001 for this one, and 10 for this one. Yeah, and actually it's only later that I will complement it with an index 11 for 00, because that if it's a bit longer, then of course I need more indices. But for now, this is the short length of my reference genome, and an even shorter length of my short read. Yeah, And that is basically what we try to do. So step 0 is what other people have been doing, and step 1, 2, and 3 is where we are actually doing to obtain a result. Yeah, and then so our research basically focuses, yeah, on everything inside this dotted line. Yeah, and that does not mean we're not looking at any other aspects, but our core research is really focusing on those aspects. Yeah, so I will not talk too much about the language because that would make it too long, but we developed our own, let's say, quantum assembler, which is called CQuasm, yeah, and QX is our simulator, and our simulator is actually a classical, it's classical software running on a classical machine, yeah, and doing simply all of the quantum algorithm execution and obtaining results. So here I will not go into the details because I will explain some of those things later on. Yeah, so you see here the Toffoli gates, the qubit definition. Yeah, you see here the quantum gate operation, the Hadamard and the index. Yeah, Toffoli gate and things like that. Yeah, so that is something that we keep on applying. And here you see the three big phases, as I just highlighted in the previous slide. Just one thing here, you see a second line, a second column, yeah, and these are because if you look at the football, the block sphere, it has 3 dimensions, so it's a 3-dimensional ball, yeah, and we do see that in quantum we want to stick to maybe 2 dimensions rather than going to the 3. In this dimension, I need to have complex numbers. And that's always a little bit more complicated to use and to compute. Yeah. So here I go to the first 2 in which I can work with real data. Yeah. Now I will not go into all of the nitty-gritty details because that would simply take too long. This is the way in which a quantum circuit can be written or drawn. Yeah. And you see here I have 5 qubits from Q0 to Q4. And the line is simply a timeline. Yeah, it goes from left to right. Yeah, and then I do a Hadamard operation, an X gate. Yeah, I will talk about these things. It's kind of the Toffoli gate, is an X gate, a Hadamard, etc., etc. And at the end, you can do a measurement. Yeah, and as I said before, if you do a measurement, you destroy basically the superposition that you're using in your algorithm, and you only get one value. So maybe I get the Q0 or the Q1. That might be one of the results that I get. Yeah. Now the amplitudes I already spoke about. Yeah, like this psi equals alpha 0 plus beta 1. Yeah, these are the amplitudes. So they describe what the most likely outcome is of this particular qubit superposition. Yeah, and these are simply all the 0 values, because in the way that we implement our quantum algorithm. All of the qubits are initialized in the 0 state. Yeah, could be in the plus state or in the minus state. Yeah, but let's say in the 0 state. So that is kind of an easy thing. And then you see that this amplitude that gets translated, as I said, into the portability, the probability. Yeah, and probabilities are always positive. Yeah, the amplitudes, they can be negative, and I will come back to that later also, because that is basically the shortcut that we can do also in quantum computing. Yeah. So step 1 is basically we have a genetic database, a classical database, yeah, with these 3 records that we have of 0, 1, 1, 1, and 1, 0, yeah, and these are DNA slices, right? So you see here the word DNA. So that is this is a DNA kind of profile that we get from, let's say, an Illumina machine, yeah, to make publicity for the Illumina again. Yeah, and there's the index. These are the 3 indices. Yeah, but if we make, let's say, all of the combinations possible, that includes also the 0, 0. So that's why I have 4 indices. So that is then, but then we super combine them. Yeah, we superpose them to each other. Yeah, how do you make the superposition? Is by doing this kind of operation. Yeah, so that basically means here you see the indices 0, 0, 0, 1, 1, 0, and 1, 1, which are those 4 that I just highlighted. And as I said, we always put the DNA, the genes in the 0, 0 state to start with. Yeah, and then we have to start assigning, yeah, the different short reads or the records in our database to a particular index. So you see here the 0, 1, yeah, which responds to this one. Yeah, yeah, is belonging to this 0, 0. So that is why, yeah, it is belonging to this one. And here we have the 1, 1, yeah, which is belonging to the 0, 1. And that is what you see here and what you see here. And the same for the two other things, yeah, such that when you combine them together, they're in a superposition. So you simply see it's basically all these qubit states one after the other, yeah. And what you don't see here in this particular, but you see them at this line, are these amplitudes. These are the amplitudes that we have for each of that superposition of qubits that we have, yeah. And if again you take the absolute value and you square it, you have 4 times 0.25, which added to each other gives you 100%, so 1 probability, yeah. So again, whatever Aritra is doing, yeah, and I will rename him quite regularly, yeah, but he tries to reason at it in a theoretical way. So simply assuming, if I have this information, what can I do with it, yeah? That does not, so that is basically whatever we see in this quantum circuit. That does not mean that this is how we can implement it, yeah? Because one, implementation at the quantum physical level is still very far away, but we're at the algorithm level, at the language level, so we can do this thing, yeah, and this is like a Toffoli gate with this hollow kind of where it means that the control, these are the two control qubits. I'm sorry, these are the two control qubits that determine whether or not you can do the NOT gate on the target qubits, yeah. And so if it's black, that means it has a value 1, and if it's white, it has value 0. So this is something that algorithmically, yeah, we have come up with, yeah. But if you want to implement it, let's say in a real quantum physical, in a quantum logical way, yeah, to run it on our QX simulator, yeah, then you have to let's say apply, let's say first an X gate so that it from a 0 becomes a 1 or a 1 becomes a 0. That is what you do with the X gate, yeah. And then you have let's say the new Toffoli reasoning here, and then you can decide or not to make the NOT operation on this Q0 or DNA 1 in this particular case, yeah. And you see you have a green kind of thing, a blue kind of thing, and a green kind of thing. And so you have these arrows, they point always to different series of implementations of the quantum logic that you need currently, yeah, for implementing this logical operation, yeah, do it in this particular way, yeah, and this operation, do it in this, everything inside the blue thing, etc., etc. So that I think is important also to understand. So let's go now into this step 1 a little bit more in detail. I have my 4 indices, as I just explained, yeah, and then I have this DNA slices in the 0 value initially, yeah, but we know that they're not simply 0 because it's 0, 1, 1, 1, etc., etc. So then we have to start assigning these things to the particular index to which they belong. So 0, 1, yeah, and I will explain also why it's assigned 0, 0, because it is what we read, what we get, let's say, from the Illumina machine, that we get the 0, 1 readout, yeah, and then we can say, okay, this is the first index, yeah, and I can do that for the 1, 1, and I can do that for the 1, 0, and for the 0, 0. So each time I can assign them to a different index in my database, basically, yeah. And then again, I have always the amplitudes at the end that describe the probability if I measure them, yeah, or the amplitude of the probability if I measure any of those things at the end to get the final result of my genetic sequencing. That is basically what I try to achieve, yeah. So here you see again that you see the graph of the amplitudes here, the blue amplitudes. So these are the probability with which one of those 4 qubits, yeah, can be chosen at some point, and that's how it's translated into those 4 probabilities, yeah, at some point. If you want to do the final measurement, it's based on the actual probability, yeah. You see here, so you see here after doing all of these operations, you do see that those amplitudes, they change, yeah. So that means that certain values, they become more or less relevant than others. And that is basically the entire logic of, the entire mechanism of quantum logic, and actually of classical logic too. But classic logic is that you change these amplitudes because ultimately that will be reflected in, let's say, a different probability once we do a measurement of those qubits. Yeah, that I think is very important that we understand that. So if we then go to step 2, which in the big picture, yeah, I have it now. The genes, the short reads, I have them in a genetic database. Yeah, and this is another short read that I'm getting from, let's say, an Illumina machine, and this is my reference genome. Yeah, so the ones in the database, and then I need to compute how well this short read matches to any of those superposition qubits in my genomic database. And then I end up with another set of superposition qubits, yeah, and that's why the color is no longer green and red, but it's yellow, yeah. So when we say yellow, always means Hamming distance. The Hamming distance means, yeah, that it's different or very very similar to what it is that what I read out from the, let's say, getting from the Illumina machine, what I see in my what I find in my database. So I see here the first one, yeah, the first index is 0, 0. Because it is basically this 0 that I map on this one, yeah, and this one that I map on this one. So that means there is no difference between any of the positions in the reads and my database record here. That's why those two elements are 0, 0, meaning perfect matching. Yeah, so this is a perfect match. And here I do that, but I have to go through. It's not that I can immediately say, oh, this is the correct thing. You always have to go through the entire database and for all of the short reads that you will get. So then I have a 0, which with this one, no, it does not match. So that's why I have an error here. And I have a 1 and a 1. There is a match. So that's why I have an error 0 there. Yeah. And so I do the same thing for the 0, 1, 0, 1. Is 1, 0, so it's difference in the two sides, yeah, and here it is the same with the 0 here, yeah, and different with the 1 that I see here is a 0 and a 1, so that's why my difference here is suddenly becoming a 1, 2, yeah. So that is the way in which I want to do the matching of the short reads, and trust me, in the human genome or in any other mechanisms, I have millions of those short reads. Yeah, and I have a billion, 3 billion of my genomic database. So that's where the enormous computational challenge comes from that we need to do. Yeah, how does the algorithm look like? So the Ham is a gate that Aritra developed, which computes the Hamming distance. Yeah, so between those two qubits here. Yeah, so similar to the reasoning I just did. Yeah, and that gives you with let's say 4 Hamming distances that you get here for those 4 superposition qubits, yeah, and they all have the same amplitude in this particular case. They have the same probability at this stage yet of the algorithm, because I'm not diversifying the Hamming distance, the amplitudes among the different Hamming distances that we get, yeah. Even though this clearly has a very very good mapping, yeah, but that will come later in the algorithm, yeah. I'll just, yeah, okay, so that is basically, yeah, how the mapping goes. Yeah, I forgot about these animations, yeah, but that's basically how we do it. Again, as I said before, this is the theoretical algorithm, yeah, and this is how we're going to implement it with the current understanding of the quantum gates, yeah, and so that is basically what we're currently doing, yeah, and so we're now in the phase where we have an X gate or something, or not an X gate here, yeah. Why is it different? Because my short read here, yeah, has 0, 1, but maybe it's a 1, 1, or maybe it's a 1, 0, and I can have multiple different versions. So so that means that this theory, the theoretical quantum circuit, may change each time I get a new short read, and depending on the short read, I may have an X gate maybe written at this line. Yeah, and maybe it will disappear here. Or maybe I have two X gates. Yeah, so this is simply the way that the algorithm works. Yeah, and that is how we do the experiments. Yeah? And if we say we, it's of course mostly Aritra. Yeah, but I'm trying to build a team again that will help in doing that. Yeah, so that means that the quantum circuit is very data dependent. Yeah, and that is also very important to realize. Yeah, that we have to be able to compute an if-then If it is the same, then do nothing, or if it is different, then we do an X gate. Yeah, so that's basically what is written here. Yeah, in this little box of the graph. Yeah, and oops, yeah, okay, and these are just the graphs. Yeah, so I said like this blue thing is enlarged in the current quantum logic, and the green box is enlarged in the quantum logic here. Yeah, and this I already explained, and that will ultimately result again in some amplitudes with the superposition states, just as we described here in the last line of these operations. Yeah, so that is this step 2. Again, that will bring me in a state vector. Yeah, and the state vector is always these amplitudes basically, and there's a vector of qubits with amplitudes underlying it. Yeah, so that is, and you see then oops, yeah. No, I will show a different one later on. So this is how we see that the amplitudes have changed again, and consequently also the probabilities have changed, because ultimately the probability is fully dependent on the amplitude. Yeah, that is very important that we realize. So next we go to the next step. Yeah, is to find the entry with the best maximum yellow, with the best matching distance, with the best Hamming distance, basically. Yeah, so in our case, we know it is the lowest values. Yeah, the 0, 0, because that means it's a perfect match for this qubit and a perfect match for this one. Yeah, so this one represents the best entry in our reference genome. Yeah. Now, where does that come from? So that you see here suddenly also a minus sign popping up. Yeah. And these are still positive pluses, yeah, positive amplitudes, but suddenly one amplitude changes its value. The sign of the amplitude changes the value, and that is also what we show here. Yeah, yeah. Okay. Well, yeah. This is what we show here. Yeah, that when we see all the amplitudes, so these stay always not complex numbers. Yeah, but here we do see that the first one corresponding to the short read, which had a perfect map on this one, yeah, suddenly gets a negative amplitude. Yeah, that is very important to see, and that's what you see also in this graph. Yeah, this particular amplitude suddenly turns from positive to negative. Yeah, stays exactly the same value in probability, because yeah, remember it's absolute value square value. Yeah, yeah, is how the amplitude is transformed into a probability. So the negative sign will disappear. Yeah, so but you don't really see that any probability changes here. So we don't really get any information at the classical probability level, but we do get already substantial information at the amplitude level. And that's why quantum logic is substantially faster than classical logic, because in classical logic we can never do that. Yeah, it's only in the classical way that we can force something to go into negative amplitude. Yeah, whereas in probability it stays exactly the same. So we don't really see that difference. Yeah, but that is why the visualization of the amplitudes is extremely important in our work. Also in building up our quantum accelerator, if we don't see the amplitude changing, we know nothing. Yeah, so that is I think very important that we emphasize again. So again, the next step, yeah, is again to get some kind of the next step in finding the best match of our qubits is then by applying Grover gate. Now Grover is a specific kind of algorithm. Yeah, I will not explain it here, but it is a way of manipulating these amplitudes in a particular way. Yeah, and here it simply means, yeah, we're going to inverse it around the mean. So the mean value is all of these amplitudes, so minus 0.5, 0.5, 0.5, and of course there are 12 other states. Yeah, so it seems like I'm only talking about four quantum states here. No, we're talking about 16 qubit states, because all of these other 12, they have amplitude 0, so that basically means probability 0. They will never be drawn. Also, if we do a measurement at some point. Yeah. So that means that if we compute the mean of those 4 numbers, yeah, and we divide it by 16, yeah, which is the total number of qubit states that I have, yeah, then this is the number, this is the amplitude or the average amplitude that I get, 0.06, yeah, and of course the minus sign now disappears, because yeah, it is divided by, well, it is added. So I have 1.5 minus 0.5 gives me 1. Yeah, divided by 16 gives me this particular number. Yeah, so I can inverse my amplitude. Yeah, by doing, say, I have my old amplitude. Yeah, plus twice the mean. So this is the mean. The old amplitude is basically this. Yeah, and that gives me my new amplitude. So then that gives me the new amplitudes for all of my qubit states, the superposition quantum states. Yeah, it's 0.65 minus 0.3 minus 0.3 minus 0.3. Yeah, because I suddenly have this minus a not be added to the twice the mean of the amplitudes. Yeah, and then that simply also holds for the 12 spurious states. Yeah, and so you see that they were before 0, but now it becomes a non-zero amplitude. So that certainly means that they also may end up being one of the 16 possible measurements that we get out of it. Yeah, I already emphasized in the beginning that when we do a measurement, we measure out of all of these 16 superposition states, but I only get one result. Yeah, and so if it's not 0, and that means I can get any of those spurious states too if I measure them out. Yeah, so that is still kind of a challenge that we have to do. Yeah, and this is the kind of logic that we're doing here. Yeah, again, I see that my complex values stay away. Yeah, it's not that I don't like complex values, but if I don't need them, I don't want to be using them. Yeah, and then here you see again how this particular theoretical state circuit was transformed into, let's say, what we can currently do with the current known gates, quantum gates. Yeah, in the language that we have, which is OpenQL and CQuasm, as I just highlighted. Yeah, and there you see again that you still have this negative amplitude for let's say the first zeros that we have of the mapping of the short read on the first qubit, the quantum record in our Genomics database. Yeah, and but you see here that the probability is not really changing, but we still see that that we still see one solution is really differentiating from any of the other states. Yeah, and that I think is very important. And then after the computation, you see all of those 0.125 for those spurious, so the zero state, previously 0 states, and what was before in this state was positive, they become negative. Yeah, and what was negative here, they become positive. So you suddenly see here also in this let's say normal probabilities, you see suddenly that everything becomes normal, but one solution really stands out as a solution. Yeah, and that is the one mapping of the short read that we got from the Illumina machine on, let's say, the record database. Yeah, so that I think is very important to see what the logic is in the genome sequencing as where we are right now. Now, you can say, yeah, okay, that's good. Everybody can make all these kinds of theories and whatever it is. But why do we still think that quantum computing is important? And I just highlighted this several times. So we can do everything in the Z and in the X axis. So without any kind of imperial college, that's a collaboration that I'm saying. Yeah, without the complex number I. Yeah, and it's only in the Y dimension that I do see that there's a Y, the complex number I, popping in, which is the square root of -1. Yeah, so if I can avoid it, I want to do that. So I'm basically in this particular part of let's say the block sphere. Yeah, that is I think important to understand. Yeah, and if we need it at some point, yes, we can adopt it. I already mentioned this in the beginning. Yeah, the error rates that we see in quantum physics, which is the red thing. Yeah, 10 to the -2. So it's we need 100 or 1,000 operations, and bang, we have an error. Yeah, and this is the 10 to the -15. This is like, so 10 to the 9 is 1 billion. Yeah, and then if you still go, let's say 5-6 times bigger than that, so this is billiards. Yeah, so we're talking about 10 billiard kind of operations before I get an error in classical hardware. Yeah, whereas we do hope that maybe the quantum physics people, they will try to really improve substantially. Yeah, maybe reach the 10 to the -4, 10 to the minus 5, etc., etc. But each time you understand it's substantial effort for them. So I understand, yeah, quantum physics, they know their challenges, but they should be more open about it. Yeah, and we're computer engineers. We know where we are, what we're used to. This is here. Yeah, but now we have to deal with that. I said, no, I cannot do that. Yeah, yeah. I don't want to be building, let's say, yeah, parallel versions of an algorithm. Yeah, because this is how I make the separation between pure parallel computing and superposition computing. Yeah, because in parallel computing, all these things, you see, there's no interconnection between a path 1 running on, let's say, dedicated memory and running on a set of processors. Yeah, other part of memory running on different set of processors, and so on. Yeah, so there's no interaction between these lines. If we do it in the superposition way, yeah, that means that there is a combination of qubit states, because there's a superposition. Yeah, and they will influence each other. The amplitudes, they will get negative or positive again. So there's clear interaction between them. Yeah, you can also this is a visualization that I made to talk to let's say potential PhD students. Yeah, and here you see the parallel way in which there's clearly no interaction between any of those threads that you spawn on, let's say, a supercomputing. Yeah, but if you really want to do it in a superposition way, yeah, then this is clearly, this depends really on whatever value is here. And this depends on every single value which is computed here in this particular way. So there's a clear interconnect between all of the computations at some point. This is another visualization. I will not insist too much on that, but this one is kind of good to see how, and this is also something that we try to understand in what we will be doing in the next coming months and years, is how the number of qubits can really grow and then start shrinking again. So here you start in 1 qubit, then it's 2, then it's 4, then it's 8, and it keeps on growing. So it keeps on growing in the number of superpositions that you have, but maybe at some point you don't need those superpositions anymore. So you throw away qubits that you no longer need, so that you may end up with a result, or that's maybe an intermediate result that you get in your algorithm, so that from there on you can start growing. So it's growing and shrinking of number of qubits as we keep on going in the algorithm execution. Whereas this is a more traditional way. Yeah, this is one path, as I said before, this is another path. Yeah, there's of course always dependency in terms of intermediate results that are given to the subsequent steps in the algorithm. Yeah, but anyway, this is how classical parallelism works, and this is how superposition works. So the big picture again, how do we position ourselves now, is in the blue box. Yeah, if you want to do fault tolerance, which we did the first 4 or 5 years. Yeah, I had people working on microarchitecture, fault tolerant, quantum computing. We did the neural networks and everything. Yeah, but now I said, it's enough. Yeah, so now we're really looking at or defining what algorithms we should be looking at. Yeah, what is the quantum circuit? Yeah, and how can we simulate these things on a machine? This is my one slide that I will show about the microarchitecture. Yeah, and this is the one that we start building actually on our platform that we will start using. And again, this is in the context of QB or the University of Porto. Yeah, but yeah, we want to be sharing multiple things, and I will come back to that at the end. We want to be sharing, let's say, a full stack implementation to anybody, let's say to Eamon or to anybody in Cambridge or whatever, if they're interested on the aspects that we're looking at right now. Yeah, and so I will not explain all of these things right now, but I will come back to that a little bit later. Yeah, but we do want to run maybe multiple of our simulators. We developed our own simulator that computes all the results of the quantum operations, even the quantum physics operations. But now also we're extending it to work on our quantum gates that we need in our algorithm, that Aritra and other people will need for their algorithm. Yeah, so that is what we do here. The blue thing is, let's say, a classical microarchitecture that we can run because in any foreseeable future, let's say 5 to 10 years, yeah, the QX simulator may become a chip, or maybe it simply stays a supercomputer. Yeah, and this will simply control all of the data coming from, let's say, some kind of local memory, yeah, a DNA repository, a data memory. yeah, from a DNA database, because this is really specialized now for our work, yeah, and then we got information. Some of these instructions, they go to the classical processor, but many of those purely OpenQL or CQuasm instructions, they go into the blue thing, yeah, and they're executed inside the quantum accelerator. Yeah, I will not go into the details. You can ask me questions about that. Yeah, but I don't have any proof of those things yet. We built a microarchitecture for semi and superconducting. Yeah, for the 1 semiconducting and the 5 superconducting qubits. Fine. Yeah, the same kind of architecture controlling 2 different kinds of mechanisms. Yeah, we can do that. Yeah, and we can keep on doing it until they reach 150, 200 qubits, physical qubits, bad qubits. Yeah, we can keep on doing that. So I said, okay, that's for somebody else to do. I want to be working, let's say, more on the application side. So that is what we're doing. I already mentioned that Aritra estimated, or that other people estimated, but he took note of it. 30,000 DNAs. So the four nucleobases. We have 3.2 billion for human beings, but only 30,000 for let's say viruses, and that can be translated into about 115 qubits in superposition or not. Yeah, for let's say the quantum algorithm that we're working. Yeah, but we do know, yeah, it's 2 to the power 115, yeah, or 2 to the power 131. So there's a huge difference in terms of capacity of these things. Yeah, and also we need to work, and Aritra started working on it also, because this de novo is a classical way of doing genome sequencing. It's not on a reference genome, but it's on, let's say, purely on the short reads that we have. And then you recompose, let's say, the overall genetic structure of the human or the organism that you're looking at. Yeah, and so we try also to look at what the quantum version is of that particular algorithm. Yeah, and all of the other columns, they're empty, because these are the things that we need to figure out as our research continues working. Yeah. Now, going towards, let's say, our platform, on what kind of computer can our QX simulator run? Yeah, and here I just give you the top 7 or 8 of, let's say, what you can find on internet on supercomputers in 2019. Yeah, and you see how much energy they consume, what operating system they have, how many processors they have. Yeah, but also what the logical memory is, the memory. And you see petabytes and terabytes. Yeah, terabytes and bytes. I think this is how big these computers can and should be to represent all of the information that we need to represent in order to have a meaningful, let's say, execution of our algorithm. Yeah, know that we have only 30,000, let's say, for only any of those viruses. Yeah, and so maybe that can definitely go on one of those supercomputers. Yeah, and this just gives you some information. So that is what we're doing. We run it on our QX simulator. Yeah, so we need a lot of memory, absolutely. We need to have a parallel execution of our algorithm, because when you have a real quantum chip, the parallelism goes automatic. Yeah. And we mentioned maybe Vazirani in the early beginning. Yeah, is a professor in Cambridge, Indian, but a professor in California. Yeah, and he said we don't really know how that superposition, how this parallel execution goes. Yeah? There is no physical explanation for that. Yeah, we do know that classically I do need a very explicit parallel version of all of the quantum gates and all of the lines of circuits that we need to execute. So that is something I cannot avoid. Yeah, so I have to explicitly parallelize my quantum software. Yeah, and only when we know what kind of qubit and when they will be available, that I will look again at the quantum chip. But that's maybe for the generation of guys like Aritra and Anarit. They will do that. Yeah. So what is the platform that we think we may need and that we try to obtain? Yeah, is making maybe a chain of supercomputers. Yeah, as we know, there are many supercomputers here in the world. Yeah, so it should not be impossible to maybe have 1, 2, or 3. I don't know how many we will need. Yeah, to combine with each other so that we have huge memory, a lot of processors that we can use to execute the quantum algorithm that we're going for. And again, to simply indicate the number of amplitudes, and I cannot even express how big this number is, yeah. But you know that this is around a billion, yeah, billion, yeah. And then so this is like ridiculously big. If we talk about 50 superposition kind of qubits, yeah, and their amplitudes that are combined with that, yeah. And 2 to the power n is simply the number of qubits. And again, this is also an incredibly large number. That's why we do need these very big supercomputers with a lot of memory, yeah. And hopefully, I will say that about that a little later, yeah. If we get enough funding, we can maybe have our own supercomputing kind of center on which we can do and make that available to other universities, organizations, or even companies that do similar kinds of quantum algorithm testing and validation, yeah. So this is just a detail. Yeah, I will not go into it right now. I told you that I would mention Atos, and it's not to insult Atos because it's incredible that a French company is being so active in quantum computing. But on the website, yeah, they do mention. Yeah, I'm just trying to get rid of the visualization. Yeah, that they really want to look at, let's say, what the quantum physical qubits can do. So yes, there is quantum noise. Yes, there is decoherence. Yeah, there are manufacturing biases, and this is good for Atos, but this is not good for me. This is not good for let's say the overall progress that we need in quantum computing. Yeah, where we have to really abstract away from all of these decoherence and biases and things like that. Simply say, no, it's perfect. Yeah, if we compute something, we know it's going to be, the computation is going to be correct. Yeah, so I do hope that maybe the Atos at some point may change a little bit in value and in vision, and also start working, let's say, towards the kind of research that we're doing right now. So I think that is a message that I wanted to bring. Yeah, and no, I do have these slides. Yeah, so so I'm at my concluding points now. Yeah, so the exponential simulation, yeah, is possible. Yeah, we can do it on QX. IBM also has a simulator. Yeah, but it has certain deficient. Well, no, it's a perfect simulator, but with a lot of constraints. Yeah, we need to really test a large number of qubits. Yeah, and perfect qubits are kind of easier because they will still use a lot of memory. Yeah, but at least we don't get any of the errors in the computations. That's what we're going to be doing. So maybe going up to, let's say, 50 to 100 qubits in superposition. Yeah, can go on some kind of supercomputer. Yeah, and we can reason about the algorithms. Yeah, and quantum computing. Yeah, we're reasoning about logical qubits. Yeah, but not about 100 physical qubits, because there you have a lot of different kind of problems, and let the physics solve them. Yeah, but I'm not a physics person, so I cannot solve them. Yeah. And so that is, I think, very important that we emphasize that. Yeah, I do mention, I just want to make one mention. I did mention, I think, Bill Gates, because Bill Gates is spending a lot of his $1 billion that he made with Microsoft on developing, let's say, vaccines for multiple diseases. Yeah, and so I do want to be able, maybe with Illumina somewhere in the background, yeah, I should be able to talk to Bill Gates. But why also, I still want to talk also to Elon Musk, yeah, not American by nationality, but South African by nationality. But he recently got into the news because he launched a rocket, yeah, not yet going to Mars, because that is what he's planning to launch maybe in 5 to 10 years, yeah, to launch a rocket like this that would reach Mars in about 8 months. So the travel of the team inside the rocket is going to be isolated for any kind of medical diagnosis for those 8 months, yeah. And then they want to be staying on Mars maybe for 5, 10, 15 years, yeah. So we also need to be able to treat them medically. So my goal is that I want to propose to Elon Musk, why not install a quantum genomics accelerator on your rocket? If you give us 10 more years, yes, it's going to be ready. Yeah, and it will be sufficiently tested, and it will be reliable, and it will not consume that much energy. Yeah, because in 10 years, a lot of the things will substantially improve. Maybe a computer will be enough, but maybe there will be a quantum chip. yeah, with real physical qubits on a very tiny, let's say, fridge, yeah, that we can install, let's say, on the rocket. So that is something that I still think is on the QB kind of mission for the next 2-3 years, to try to reach, to talk to Elon Musk and to Bill Gates, yeah, about this kind of research. So this is basically the talk I wanted to give, and I'm willing to answer any question that you may have. Yeah, and if I made an error in explaining things, it's my fault, right? I'm just responsible for what I expressed myself. Thank you very much. I don't hear you, Eamon. Yeah.
Getting back up.
Yeah.
Wow. Look, first of all, Koen, that was absolutely incredible. Now, I know an awful lot of you will not be able to follow everything Koen has said. I just want to say, you know, don't worry about that, because if you can follow essentially what he was saying, because I mean, he lost me in so many areas, because what he's doing is absolutely.
Because your cable has slipped back here and it pulled the cable out, so it's disconnected.
Oh,
You have to reconnect.
oh no.
Sorry about that.
What do we have to do? End it off.
So it's because it's reconnecting to the internet now.
We may explore in the short term this kind of use cases on genomics with quantum. So and we are going to be co-located with Illumina and Genomics England, because we are going to be in the Genome campus in the Biodata Innovation Center. So it's an emblematic location to inspire this kind of discussions. So really delighted with your talk, and really looking forward to have a further discussion with you about the ways to collaborate together.
Thank you very much, because it is in no way no criticism on Atos, right? I mean, but it's very good that Atos, one of the few European companies really moving in that direction. Yeah, and if you mentioned, because I thought you mentioned Illumina too, right? This is related to this Cambridge Center, or may try to become related, or is that, did I misunderstand you?
Yeah, you know, in the Genome campus, where we are going to be located is in the Biodata Innovation Center, which is like an incubator. Okay. In that place, Illumina is also based, and Genomics England. And this is the part of Illumina working for the 100,000 genome project, which has become the 500,000 genome project. So meaning that there are a lot of things to explore together, and we are excited with the possibility to start those discussions. It's early stages, obviously, because with this lockdown period, we were not able to open our center or to make any kind of announcement, but it would be coming soon.
Yeah, well, the only thing I may have mentioned in the beginning is that the BlueBee company that I started so many years ago on genomics, yeah, the current CEO, Hans Kobbe, he will become now one of the vice presidents of Illumina. And so there may be a close relationship now, because this is a good friend of mine too, Hans. Yeah, so and maybe there's a way that is simply hypothetical, right? There is nothing concrete, that maybe Illumina would invest in QB to stimulate our research also in the quantum genomics, because if it really proves, as Aritra is showing, that indeed there is a huge potential of doing that, then that opens up the possibilities for almost every single country in the world. And now I'm really thinking about, I went a lot to Africa, to Mali, yeah, and you're French, so it used to be a colony, yeah. So they don't like the French anymore. But like Congo, we were the colonial properties of Congo, yeah, Zaire, yeah. So they don't like the Belgians either, yeah. But with Mali, and I think I want to do that maybe with multiple African countries. Why shouldn't they send maybe one or two, let's say, either engineers or medical people to study the quantum genomics, what we're currently doing, Yeah, and we do that in an international context. Given all of the COVID-19 kind of, no, I would not say stupidity, but the harassment that we got from it, not that it's such a deadly virus, but we need to be ready. Once it is really a deadly virus, it's going to kill millions of people, hundreds of millions of people. So in that sense, it would be a great way if we could continue talking to each other. You can ask, maybe Iman will send around my email. It's not my TU Delft email. I don't have a QB email yet, but my personal Gmail you can use, and we can keep on interacting and establishing a contact. Maybe I come to Cambridge and give a talk there, or we discuss it. So that would be very interesting. Yes. Okay. Thank you.
Great. I will leave you my email in the chat.
Okay. Thank you. Yeah. Thank you.
Thank you.
Koen, I wonder if you have the chance to try this algorithm in the Atos QLM. Have you made any trial on that?
No, nothing. We just we still want to do a first kind of set of test demonstrators in the next 2 months. So if we can have access to an Atos machine, I would be super happy about that, right? Let me be very clear, yeah? Yeah, but we have not even tried, because I tried to submit a project, and that's maybe 2 years ago, and then Atos immediately said, no, we're not interested, yeah? So it's fine, everybody can make choices and has interest, but we would love to have access to, let's say, a good machine that is used to executing quantum gates, yeah? But of course, the only thing that we have is that we have our own language. So we compile we have a version of our QX simulator, yeah, but it's in C++. So that should also be able to run, let's say, on an Atos machine, I think. So yeah, if that is possible, if you also would leave your email on the chat, I will contact both of you for this.
Okay.
Yeah, thank you very much for offering.
Yeah, thank you.
That's wonderful. Any other questions from the audience?
Yeah.
Hey, hi. This is Muni from Singapore. Can you hear me now?
Yes. Hi, Mani.
Good. I mean, I know this is more for the European talk, but thanks to the COVID, right? You're organizing it remotely. I could able to connect. The question here is, are you in touch with any of the Asian institutes? Because last year in December, if you've seen in Nanyang Technology University from Singapore, they published the genome sequencing for the Asian race, right? And then our Singapore Center for Quantum Technologies are in collaboration with them, and then making this data available, et cetera, et cetera. So just getting from that sense, are you in touch with any of the Asian peers and trying to expand your the research towards Asia?
So I've been very open, because I had like two Chinese PhD students that graduated already, yeah, and one of them is in London actually, and the other one is already back in China. He's an assistant professor there, yeah. And I have one Indian guy. Well, Arita, you know him now, yeah. And I have one master student who's also Indian. Yeah, and yesterday I think I spoke with the lady. I always forget her name.
Ashita.
Ashita, yeah. And I always try to encourage her if she's interested. I do hope that I will get substantial funding for this kind of research, and then then I do hope to be able to attract good students to come to Europe for a short time. Yeah, but I don't have any contacts yet with China a little bit, yeah, but I know that China has the Beijing Genomics Institute, BGI.
Sure,
yeah,
BGI.
But they're not interested. Yeah. They're not interested on quantum yet. Yeah, so that is a bit too early for them, I think. But no, so that is definitely interesting. But we're just starting, so we're tiny, small. So nobody wants to talk to me. You know, I do hope. I'm very glad that Atos wants to talk to me in Cambridge. You know, so that would be already a fantastic achievement. But anything else, I'm open, but for now it's very difficult. Yeah.
So in Singapore, there's also Entropica Labs, which
Entropica, correct.
Yeah, so they started looking at quantum genome sequencing. Like that was one of the first things that they wanted to look at as a startup. But now they have like shifted a bit away from genomics, and they're looking at more fundamental problems. So they realize they need to solve those first before jumping into the application domain of genomics. So that's another group that initially I was like talking with them on LinkedIn. So like collaborating, they were basically doing very similar things that we were doing, like mostly on the de novo genomics part, the quantum mapping of that. But now they're looking at different things other than genomics.
They're based in Russia, right?
Entropica Labs is based in Singapore.
Entropica.
Singapore.
Yeah.
Okay.
Yeah,
so
Protein Cure is
from
based
Singapore.
in US. Yeah.
Okay.
Correct. I'm from Singapore. See how we can open up the doors, right? I'm in touch with my government here, which is quantum, the quantum wing of the government. And also we have NTU, which also sequence the Asia-wide genomic, right? I'll connect with you in the LinkedIn and see how we can open up and open this part of the Asia, right? And then we can take it from there. Okay. But excellent topic. I've learned a lot. Thank you so much.
Yes, look, I think this does have worldwide reach, obviously. By its very nature, it's got a worldwide collaboration, and Matteo and I want to talk to you as well, Koen, about the Australian side of things and the supercomputing center we have here. So look, I think everybody is, and it's very exciting. Please contact myself or Koen, and we can get everybody talking together and working on this globally, because it's a global issue. Is that fair enough, Koen?
Yes, absolutely, and I'm willing, and then I will involve maybe more Aritra in 1 year to update everybody a little bit on our findings, and maybe also what I did not do right now is to highlight what stack we make available, like the language, microarchitecture. There are a lot that we already built. Why not use it? Yeah, and it's not that I want to have, let's say, 50 languages, because there are too many quantum languages, to be honest. Yeah, and everybody needs to go in a particular direction, and everybody makes a lot of claims, and nobody can verify anything from each other, and that I think is very bad. So that's why if we end up with, let's say, one open public domain kind of platform that multiple universities, organizations look at, and maybe that a company like Atos could be a supporter of part of it, yeah, that would substantially improve international collaboration. Because if we understand one thing from all this COVID-19, if we don't internationally collaborate for those kinds of problems, we will never find a solution. Yeah, and I think that is for me also an important message that I wanted to bring today. So that I'm highlighting maybe too much now, but okay, that nevertheless important.
I think that's an excellent point, Koen, and there's, for everybody else in the audience, there's collaboration is happening worldwide. A lot of companies are putting educational resources and training resources and information, not the same as what Koen's doing, obviously, but everything is going into open source and into collaboration. There's two things globally that every high-end quantum consultant talks about, and that is speed to market and collaboration. We need both of those, and as Koen mentioned, it's speed to market is somewhat out of our hands, but even though the quantum computer is capable of mind-boggling computations, it is very, very fragile. And there's an awful lot of work to go into it. One thing I would say, possibly on an optimistic note, is that I have found in the quantum world that things do happen quicker than we expected. I mean, if you look at supremacy, now you can say whether it happened or whether it hasn't, because it wasn't a meaningful task that was conducted. It was merely a random number generated, which we know quantum computers are good at. So it was a little bit biased, but irrespective of all of that, a quantum computer, the Google-NASA collaboration back in, was it October? Oh, I think it was this year. But anyway, last October it was reached. So I can remember just talking 10 years ago to other quantum researchers, and they were talking about, number one, would we ever build a quantum computer? And number two, would we ever beat a classical digital supercomputer? And they were talking hundreds of years. I remember it very well. And already we've made leaps and bounds. So that's not to say that we're going to carry on with this acceleration, but the more people we have working, the more people we have collaborating, the more funding will come that way and the more will happen, because we will get there. We will get, you know, it may be 50, 60 years, but we're going to get to a wonderful, very, very interesting stage where what we're talking about now becomes real. So I don't know whether, Koen, you want to add to that? Or?
No, I just want to maybe I'm repeating myself now, but just know that the transistors, the first one, the idea of a transistor was written down by a German engineer in 1934. And then it took 40, 50 years before we had an industrial scale, very large scale integration. So, and we don't even know what a transistor or what a qubit we need to what we will be making them of. So we still have like maybe 50 years before we reach, and of course things will speed up at some point, but we still have to make a couple of really fundamental choices before we go in a particular implementation direction. But we should not wait. That was the two graphs I showed in the beginning. We can start descending down and working in, let's say, perfect qubits simulated on, let's say, the Atos machine. Why not? Yeah, that gives us as good results. Yeah, and we hope to show those things in 2-3 months, because we're running some of those experiments on maybe an Atos machine. Yeah, let's be very clear. Yeah, I will contact you on that. But otherwise it will be on a machine in Amsterdam or wherever it is that we have access to. But international collaboration is extremely important, and time to market. Nobody should think that it's 5 years. It's more 10, 15 years for quantum accelerators, because that is understandable. Yeah, but anything else, is the talk of publicity guys and marketing specialists, but not of me, at least.
Yes, totally understood. Are there any more questions? Because we've gone a little bit over time, but I think we'd all agree it was absolutely wonderful. Koen, absolutely wonderful presentation. You know, your knowledge and your humility is wonderful. Is there a question?
Yeah. Microsoft came up with their own language. IBM came up with their own quantum language. And Google came up with their own quantum language. It's like which one to follow? That's the major basic thing. What the question is, which language to follow?
Look, I'll answer that, Koen, if you don't mind. Look, yeah, it's a great question, and nobody has the definitive answer when it comes to hardware or the accompanying software, which is going to take off. During his talk, Koen spoke about ion trap quantum computers, superconductivity. There's topological qubits, which is the Majorana, which Microsoft has gone. You know, no one knows which is the right way. And the important thing is scalability. So, for example, superconductivity is up to around about, depends, you know, it's around about 55 qubits. It depends, you know, what news you're looking at. Whereas the topological is still only about half a dozen qubits, but it's going to scale amazingly. Honeywell, who are using the ion trap, Honeywell have given a projection of, remember Moore's law that doubles every 18 months? Honeywell with their ion trap are talking about a factor of 10. So that's why it's all amazing, and it's a race, and we don't know which hardware is going to get there. Most of the software is being written. I mean, you're probably talking about Qiskit for IBM and Q# for Microsoft, and there are many others. I won't mention them all, but a lot of them are becoming platform independent, simply so that they're not tied in to whoever's going to win this race. And it's going to be very interesting because they're all putting, as Koen mentioned, they're all putting billions of dollars into this technology. And quantum computing is going to be something where there is going to be a winner. There's going to be something that just simply computes more purely with a better fault tolerance. We're using, as you know, NISC computers at the moment, so they're noisy intermediary. So besides the hardware, there's the error correction software, which is going to improve. And there's also methods of not needing, having a qubit at room temperature rather than having all the dilution refrigerators. Look, that's a bit of a roundabout way to say no one really knows at the moment. Now, if anybody else would like to, I mean, if you asked, well, and photonics as well, but has anybody here got an opinion on what's going to win the race? Aritra, do you have any comment?
Well, a lot of these tools are now working on cross compilation. So if you learn any one of them, I think within a few years, we'll have like cross compilers to different languages. So if you focus on only one of them, what's more important is understanding how the logic of the programming works. And then you can just pick any language, whichever you find is good. And then you will be able to target any hardware platforms that will come up in the future.
That beautifully said. That's what I was trying to say. It's going to be platform independent. The bigger race is which hardware is going to win.
This Atos has been mentioned several times here. I have to say that the way that we intended to build our simulator, it's as an open topology platform. So it's not, as many others do, it's a language for their own implementation of their test machines. We're doing something that it's platform agnostic. And we built a kind of connectors to be able to import and export from different languages. And at the end, we are relying in the quantum, in the QASM standard internally. So, well, we realize that this is a problem, and normally when new technologies come up, standardization, it's an interesting point. So this is why we try to make it as much as open as possible.
Thank you very much for that input. That's and again, couldn't agree more. I think we're all essentially saying the same thing. And so they're developing in different paths. I think, Albert, do you have any feeling on the hardware? I mean, is Atos? I'm sorry, I'm not aware, but are you developing hardware as well, or is it just the software?
Well, we are not, let's say, participating in the race of generating new hardware. You know, this requires very big amounts of money for doing that, and it's always only in few hands doing that. What we are doing is we are preparing the software layer for that. We have a hardware simulator, which is, let's say, classical technology, able to simulate up to 40 qubits. And as Koen mentioned, our idea is that the very best thing that we will have will be quantum accelerators, not full quantum computers. So our idea is that our quantum simulator will be able to have some kind of hardware plugin, like now we have with a GPU accelerator. At some point, we expect to have a QPU accelerator, and our simulator will be able to use this specific hardware to accelerate the quantum pieces of the algorithm that it means. And I only can mention that through some partner, we expect to have something in this way, in a quantum accelerator by 2023.
Wow.
But, you know, right now this is something that it can be 23 or 24 or you know,
Yes.
who knows.
Yes. I mean, look,
Yeah,
yes. Thank you very much. Well, I think as long as I mean, Prabhu, that was a great question. Thank you very much for that. And I think let's all keep in contact. Now, you can contact myself or Koen, and we can, you know, let's all keep in touch and see how things develop over the next couple of years. Are there any more questions from the audience?
I just have one single question.
Yes, thank you.
That was about like, yeah, actually, since we are like talking about quantum accelerators, so I was thinking like if we are talking about using those quantum accelerators with like classical machines, like if we could generate or we could like research about a operating system about those accelerators separately, can we be able to use those accelerators as separate like heart of the machines?
Koen, did you hear that?
Sorry. Oh no, sorry. The last part of your sentence I did not fully understand again. So,
like, can we make the quantum accelerators the main part of the machine, like the main processor of the machine?
well, I think a quantum accelerator, if in, let's say in 10, 15, 20 years it will be available, it will be something that you can put in a data center. So that you can program something and say, oh, I want to have a quantum computation and do this thing, yeah. But so it will become maybe it will become even as invisible as an FPGA or a GPU or any other kind of processor device. So that is for sure. That is what we are trying to do also now in our current research. That's such that there's a little drawing that the microarchitecture I showed, and the QX is basically the quantum accelerator part. Actually, the blue part is also quantum accelerator, but it should be blind. Yeah? Everybody should be blind for using a quantum accelerator or not. It should be automatic. Yeah, and that depends more on the programming language. Yeah, like Prabhu was I think it was Prabhu, right? Yeah. So if those languages they support that, that's fine. That's what Atos also I think hopefully will start supporting much more. Well, he's already supporting. Yeah, but that will be the automatic way of connecting quantum with the classical computer in that way.
Yes, but like exactly here we are like talking about the computers and the laptops, but like in some of the machines, like for example the robots, where like the direct interface is not required, just the processing power is required. In that case, can we like use accelerators directly as the main chipset of the machine?
If the robot, you're talking about robots, right?
Yeah.
Yeah. So if the robots can connect, let's say to let's say the remote server, yeah, the language should allow to do that, to send data, yeah, and then it computes a result and sends back the result. That is possible, just like we do it now, yeah. But having let's say a quantum computational device embedded inside, yeah. Don't forget that you need almost like 2 meters. Is a helium fridges, yeah. So there is no way that you can build that, but there is downsizing that too. But that may take another 5 to 10 years, and then everything else needs to follow too. So I don't think that is kind of a realistic kind of approach, yeah. But the remote connection, sure, that is possible.
Because since we have been like learning about the NLP and the like AI into the quantum algorithms as well. So I was just thinking it's just a matter of time, like when quantum algorithms meet the robotics part. and like when the robotics algorithm will start using these quantum languages and algorithms to process the information?
You asked me to make predictions, eh? And that's very difficult. I already make a prediction about quantum and keep on doing it. Yeah, but I think it's always going to be a helping instrument for anything that the humans will make, be it a robot or a car or yeah. So I don't think that it will ever dominate. Eh? You already have maybe some journalists maybe that say, yeah, supercomputers are most powerful. We don't need humans anymore. I say, well, okay, I don't think so. Yeah, so that is very difficult to make such kind of prediction, but it will be for sure a very interesting kind of and helpful kind of instrument that we can connect many devices to. That I do believe. But that is again, shoot me if I'm wrong, eh? But that is my prediction.
I mean, the other thing is that, Ritwik, you're a lot younger than Koen and I, so you may well see things happen in your lifetime that we don't. So we need more people like yourselves thinking outside the box, because as we all know, if you think outside the box, it generally follows that we start doing it. I mean, Koen and myself were talking the other day. I can remember when, and this is just early 80s, you know, just when I was with Apple for over a decade when Apple computers first came out. And we were talking about video conferencing and how one day we will do video conferencing. And I remember it clearly that we never thought it would be in our lifetime. So having this technology embedded in robots, in drones, and all of these fantastic technologies, you know, we're not saying it will never happen, but it's a long, long way off. And but the more people we get into the industry, the more ideas we have, the more we focus, the more these things will happen.
Yeah.
Okay, look, why don't, it's 8 o'clock, we've had 2 hours, it's been fascinating, and I'm sure everybody would like to join me in thanking Koen for an absolutely incredible presentation. I'd like to thank Matteo here next to me, who's been keeping you all updated with links. And let's, it's probably a good idea if you contact anybody who's got ideas or wants to follow up, contact myself and Koen, and then we can coordinate it throughout the group, and we can set up a Slack group, we can do whatever we need to, but let's keep in touch and let's make some of these dreams happen. Again, I'd like to thank Koen and Aritra and Matteo, and from me, this is me signing out, and thank you everybody, keep in touch. Keep in touch.
Okay,
See you
Okay.
all again soon.
Thank you very much. Thanks. Bye.
Pleasure, Albert. Lovely to meet you.